Welcome to Developing Graphics Frameworks with Python and OpenGL, Part 19, Translation Matrices. In this video, we're going to learn how to represent translation with a matrix, which might sound easy, but it turns out it's a little bit tricky and will require us to use something called homogeneous coordinates. So, to begin, translation transformation adds constant values to each component of a vector. So for example, this transformation adds the constant values m and n to the x and y components of a vector. Now, it can quickly be seen that this transformation cannot be represented with a 2x2 matrix. As a simple example, let's consider translation by the vector 2, 0. And so m equals 2, n equals 0. Now, if this could be represented as a matrix transformation, right, the matrix ABCD times XY, well, that calculation looks like this, and we should be able to solve for the values in the matrix A, B, C, and D. That should be equal to x plus 2 and y. So if we start matching up coefficients, the coefficient of x is 1, so a should equal 1. The coefficient of x in the second component, well, there is no x, so c should equal 0. The coefficient of y in the second component is 1, so d equals 1. But by process of elimination, that leaves us with b times y must correspond to 2, so b equals 2 divided by y. Right? That's not acceptable. The values in a matrix should be constant values. Now you might say, well, what if we just let b equal 2? Then we'd get something called a shearing transformation. Right? So if this was the matrix 1, 2, 0, 1, it would take square grid like this and kind of shift it over to the right. Right? So shearing is almost a translation. The points along each line are being translated by a different amount. Right? So if we used this transformation here, the points along the line y equal 1, right? If y is equal to the constant 1, then we get x plus 2. Right? So that line is getting translated by 2. The points along the line y equals 2, if we put the value 2 in for y, those points are translated to x plus 4. Lines along the line y equals 3. Well, if y equals 3, then we get x plus 6. So each line is translated by a constant, but a different amount. However, there is something redeeming about this observation, that the points along the line y equals 1, that is to say, points of the form x comma 1, they are being translated the way we want them to be. And so, this is going to cause us to shift the way we think about points. So, for example, consider translating a one-dimensional space. If we just wanted to translate the points along the x-axis, we could identify those points with the values x comma 1 and use this matrix. And so the idea to be able to use matrices to represent transformations is to embed a space in the next higher dimensional space and make that extra coordinate equal to 1. So for example, we can represent a one-dimensional translation with a 2x2 matrix. We just have to identify the point x with x comma 1. And sure enough, if we multiply this matrix, 1, m, 0, 1, by the vector x1, we get the vector x plus m, 1. So x is translated the way we hoped. If we think about two-dimensional transformations, we're going to use some analogous reasoning here. To translate points in the plane, so a point xy, to translate that by the vector mn, we'll identify the point xy with a point in three-dimensional space, xy1. And then we can multiply that vector, xy1, times this matrix. And the result will be x plus m, y plus n, and that extra 1 at the end. Right, so we're thinking of embedding the two-dimensional plane with the set of points in three-dimensional space where z equals 1. Traditionally, you might think about identifying the plane as the set of points where z equals 0, but for the algebra to work out, we're going to make that extra coordinate equal to 1. Now, the great thing about algebra is it generalizes very nicely. Let's say we want to translate points into three-dimensional space. We'll use the same kind of reasoning. We'll identify the point xyz with the point xyz1, and to translate by the vector mnp, we can do that by multiplying by this matrix. So even though there's no intuitive way to visualize 4 spatial dimensions, we can still do the algebra. Now, this way of thinking about points and coordinates, these are called homogeneous coordinates. Right? So, and we need to use these if we want to represent translation as a matrix transformation, which we very much want to do. So as we saw in all those examples, we'll embed a space that we want to translate in the next higher dimensional space, and we'll set that new final coordinate equal to 1. Since we're mostly interested in three-dimensional graphics, we're going to be identifying the point xyz with the point xyz1. And incidentally, this is why in a vertex shader, we're working with vec4s, with four-dimensional vectors. This explains that mysterious 1 coordinate. Now, one thing you might be wondering is, well, what if that last coordinate was not equal to 1 for some reason? Well, it turns out, if you have a homogeneous point, xyzw, that corresponds to the three-dimensional point, x divided by w, y divided by w, z divided by w. In other words, the first 3 coefficients, or the first 3 components, are divided by that 4th component. And that transformation is called perspective division. It's not a linear transformation because we're dividing by this value, but it's a calculation which is automatically performed by the GPU at the end of the vertex shader processing. And so, hey, we've got a way to do translations. But is this system, or using homogeneous coordinates, is that compatible with the rotation and scaling transformations we discussed in the last video? Well, it turns out, luckily for us, it is compatible. And previously, we looked at linear transformations, which can be represented with matrix multiplication of this general form, f of xy equals ax plus by cx plus dy. If we want to write that in homogeneous coordinates, we have to introduce a third coordinate equal to 1 for the input, and the third coordinate for the output should also be 1. And sure enough, this function here on the right, this three-dimensional function, can be represented with matrix multiplication in this form. In fact, it looks like the original 2 by 2 matrix is embedded in the top left corner, which it is. When using homogeneous coordinates, you can actually represent all 3 transformations in a single matrix. And those 3 transformations, translation, rotation, and scaling, and I guess shearing as well, they're all collectively referred to as affine transformations. And you can represent them with a matrix of this form. So the top left corner, this 2 by 2 matrix with the A values, that corresponds to either the rotation or the scaling part of your transformation, or it could be the identity matrix if neither scaling nor rotation is occurring. This rightmost column over here, M1, M2, that represents the transformation by translation. Right? If you want to translate by a vector M1, M2, you would put those values in here. Or if there was no translation component, of your transformation, those values could both be 0. But again, homogeneous coordinates allows us to use a unified data structure, a single matrix, to represent all these different kinds of transformations. And we can also combine these transformations using matrix multiplication. So it all works out very nicely. Now, that's a two-dimensional transformation, but of course, it generalizes well to 3 dimensions. Right? In 3 dimensions, we're using a 4-dimensional point, x, y, z, 1. And so as long as we're using homogeneous coordinates, we can represent all the transformations we're interested in with this 4x4 matrix. Notice, just like before, the last row was all zeros and a 1. And in the previous slide, 2 zeros and a 1. That's to make sure that last component stays with the value 1. But within this matrix, the top left 3x3 matrix contains any rotation or scaling transformations that have occurred. And within this rightmost column, this gives you the translation component of your transformation. And so that's how we can represent not only translations, but all the types of geometric transformations we're interested in with a single matrix, thanks to the use of homogeneous coordinates. Now, there's one more kind of transformation that we're going to need, not for moving objects around the screen, but to give us that perspective effect, a perspective projection transformation. And it turns out that using homogeneous coordinates is helpful for that too. But we'll leave that topic for the next video.